All right, so let me start reviewing and do video stuff. So I was kind of slow last time, and then I realized I probably will not finish this derivation we're doing of a light bulb. I need to make it kind of look like a light bulb best that I can. Remember, we're talking about square light bulbs. And again, this is because there's a lot of really good quantum mechanical lessons in a light bulb. So we're going to cover this stuff. And we're ultimately trying to get to the energy output of a light bulb. That's the end goal. Because that's easy to know what that is. It's measurable. We should know enough about light and energy to do it. That's the idea. Remember, it's around 1930 or so. And so that's the end goal. There's a lot of quantum mechanical lessons in here, and unfortunately we're going to hit a couple of complications today. To be blunt, this is going to get kind of hideous, all right? If it wasn't already, it gets worse. I'm not even going to be able to finish it today. I don't think I'm going to be able to finish it. And so you're just going to have to roll with that and, try to watch the videos as well. But you have your notes, you have videos, maybe you bought the book, maybe you didn't. I hope not, because I want to save you some money. But anyway, so because of the complication of this, let's review from the beginning. Okay, light bulb, I made it square to simplify the fact that we're going to describe waves in it, and because we're in 3 dimensions, that's why I made it a cubic light bulb. It's a little weird, but the reason was we think of light, so I know there's light in it, and I think of light as waves. We talked about that last time. And I know that sines and cosines are waves. I like sines more than cosines because the derivative is cosine, which is positive, and I don't like cosines because the derivative is minus sine. So I try to use sines, it doesn't matter. And I know that we looked at a bunch of waves and we came up with this formula for the waves that fit in the box. That's another supposition we have to have. I've tried to do this a little bit better than waving my arms around like I did last time. A wave like this, and a wave like this, and I'm doing half waves, and then there's one in Z. So I tried to draw that best I could. And so that's a wavelength of L over 2. That's the smallest wave that fits. Question?
Why is a cube better than a sphere?
Because it's easier to delineate, to divvy this up into X, Y, and Z. And it's just hopefully a little bit more clear. And it's kind of natural to think of this as a cube. It works for a sphere too. In fact, it's entirely identical. It's just like, when I see X, Y, and Z, I just immediately think cube. So that's really entirely why I'm putting it that way. So, but it truly does not matter. Actually, another way of saying that is cubes are easy to work with in X, Y, and Z, and spheres are easy to solve in R, theta, and phi. And this is easier to solve with X, Y, and Z than R, theta, and phi. When we get to quantum, hydrogen atoms and stuff, everything has to be in R, theta, phi. Atoms are round. You don't have a choice about that. Okay, so again, this is the formula for our waves. N equals 1 is a half wave, which fits in the box. They have to fit in the box. Okay, so that's all sensible. And then we had to get down the rabbit hole a little bit, which is to look at Maxwell's equations for E and M, if we accept those as well. I've written this out a little differently on purpose because I kind of want to get you used to what differential equations look like. They're often expressed this way. And you are supposed to know that you're supposed to fit the function, which is here. Remember, this is the electric field, not energy. We will also run into the problem of running out of letters. So this is the electric field of light. You're supposed to know that you got to put the E in there in each term. Okay, so this looks like a bit of a bear. The other thing to note that as much as we understand, sine of X and Y, remember that I could have, why not say that it's sine X plus sine Y plus sine Z? Or maybe it's sine X plus Y plus Z. Why is it sine X times sine Y times? Why is it times? And the answer is something we're going to see over and over and over again. And I mentioned this last time, but I kind of need to mention it every day. This is what you call separability. This is a separated differential equation. Don't worry about writing it down. You'll have to later, not today. but this is the first example of a separated differential equation. That means that there's this term that stands by itself with only x's in it. Here's one with only y's. I don't see derivative of a y times x. I don't see the derivative of y squared plus z squared. It's all by itself. This is by itself. The t is all by itself in its own separate term. And that means that that this ends up having to be a constant. This has to be a constant, this has to be a constant, or it just won't work. Or, now remember I said this last time, I am reviewing myself. If it's not a constant, then the change in x has to perturb the change in y. So if a ball is going down a platform and it veers to the right, then it's going to have to also veer forward or backward at the same time. Now that, you're thinking like, well, how could that happen? Right, it can't. No, that's ridiculous. So because of that, all these terms have to be constants, and the only way that's going to work is if these are multiplied together. And you'll do a homework where I will have you try sine x plus sine y plus sine z, and you'll try that in something like this, and you'll see it'll fail. Not on the next homework, but soon. So anyway, again, something you kind of have to accept. Okay, now you plug this thing into that thing, and again, still reviewing, and what did you get but this? I'll start over here. Just note that I'm working down. It's not particularly difficult, so we're starting to shave these hideous things, as we will almost always do, except when we get to the quantum mechanics of the hydrogen atom, which is always hideous, always hideously long. There's no shaving that one down, but all the other problems we have start out huge, and they'll always be shaved down to something that's like 5 or 6 constants times e to the energies. It's always turns into something like that. So anyway, all right, we plug in the electric field equation into the Maxwell equation, and we get this. Notice that I did get it to spit out constants. Right now, remember I said that when you have this separated differential equation, each term has to be a constant. In that way, they can't different dimensions don't mess up another. A change in one dimension, a change in x doesn't cause a change in y, which is nonsense. And that works if everything is a constant. Note that it's a constant for a weird reason, though. Now again, I did this last time, but you know the double derivative of x causes all this stuff to spill out, but the functions are still there. This guy, the functions are still there. So all the terms, all these Maxwell equations still had sine xyz, sine xyz, sine xyz, sine xyz, oh, don't forget t. And so they all canceled out, leaving behind a bunch of constants. So I was right when I said that each term is a constant, but for weird reasons, because all the other terms, the function, it's like it boomerangs back, right? So that's the cool thing about a sine function. If you take the double derivative of the sine function, you end up with the same function. And since all the other terms did that, all the functions cancel, and you're left with this. So anyway, look, it's kind of brainless, right? I'm just harking on this because it's going to come up again and again and again and again. This Maxwell equation deal, this is almost identical to the Schrodinger equation. And by the way, this model for an electric field, that's what we'll call a wave function in the future. Don't write that down though. All right. Now what I've got is something that remember these are called modes, and they tell us the number of, the modes tell us the number of nodes, right? If nx is 1, there's no node, it's just a half wave, there's no node in a half wave. So also, you know that tells you the wavelength. So this is just reaffirming that. This is allowing me to figure out what waves fit in the box and therefore have what wavelength. So the wavelength is dependent on the number of nodes of the wave, but of course it is, right? So this is an aside. I'm just redrawing what I did last time. No nodes means that the wavelength is 2L. It has to have a wavelength of 2L to have no nodes, right? If the wavelength is L, then there's one node. There has to be one node, or it doesn't work. So anyway, so that's what this does. That's what this does for us. Okay, now it turns out that I can make this a little bit easier by giving this a net just like our Jacobian in x, y, and z, remember when we did dvx, dvy, dvz? Yeah, I showed you how to turn that into net, the partial of net velocity. So it looks like we have kind of a similar situation. We've got this index that goes, 1, 2, 3, 4, 5, 6, 7 to infinity. I've got 3 of them, and so I can call them, I can give them like a radius, right? This is like a radius. The radius squared is x squared plus y squared plus z squared. So this n squared is x squared plus y squared plus z squared. Now what's nice about that is that now I can do this. N squared is 4L squared over lambda squared, and therefore lambda is 2L over n. So what's cool about this is that I can take these three-dimensional waves, give them an n, and I mean, look at what I drew up there. 1 squared, 1 squared, 1 squared, n squared is 3, right? So now I know the wavelength. 2L over the square root of 3. I won't write that down, it's a little complicated. I hate square roots, but anyway. Okay, so that's what I've done. So I've shown that the signs, when I multiply them properly, make the Maxwell equation work. It spits out a bunch of constants. And I'm able to relate wavelength to the number of nodes, or the mode number. Those are the same thing. But I kind of designed it to do that, so that shouldn't be strange. But now, remember that what we're trying to do is get to the energy of the light bulb. Now here's a big hint. I got the wavelength now. So that's huge. Sounds like I'm on my way to get energy. Question?
So if you have half a wavelength, you have 0 nodes, right?
Yes. And
so how do you divide by 0 if n's on the...
No, the mode number, no, hold on. Mode number is 1.
Oh.
Right, mode number is 1. Right up there. Right, so that's kind of a trap, right? Notice that, remember our equation for wavelength? It was 2L over n. So when I draw n equals 1, which is only half a wave, I give it n of 1, the wavelength was 2L, like I had up here. So that's a bit of a trick to avoid that problem, by the way. So we start, it's a little counterintuitive. When we count up, 1, 2, 3, notice I was talking earlier, 1, 2, 3, 4, I didn't say 0, 1, 2, 3, 4, it's because I was thinking of that. So, okay, now again, I've got a lot of this stuff parameterized. Now I want to get to energy. And note that this is where it actually unfortunately gets hairy. I know it seems like, well, I know that I have the wavelength, and I know that light's energy is Planck's constant times the frequency, which is actually related to the wavelength. It looks like we're almost done, so we're kind of not, unfortunately. Let me write some equations that are logical, like for total energy. So the total energy, and I'll be careful about not calling it E, by the way, because I've already used E for an electric field. And this is ultimately going to be temperature dependent. Let's see. The first thing is there's actually a degeneracy factor here. There's a degeneracy. Now, leave some space, you'll see why. So here's the thing. Remember that I've got wavelength in terms of this net vector. And that's awesome. It makes this easy, except that I introduced a problem when I did so, which is a degeneracy factor. Now let me show you what that means. Now, remember, this is an aside. Now, when I have the set 1, 1, 1, which is what I drew up there, how many ways can I write that? Now, that gives me one wavelength, because that makes n squared 3. And so that's the square root of 3. And there's one wavelength for that. And how many other ways can I write 1, 1, 1? The set 1, 1, 1. Just one. Right, just one way. Now here's where, now you're going to see where it gets confusing. What about this one? Right? How many ways can I write that are equivalent? Huh?
1, 2, 1, 1, 1, 2.
Right, so 3.
How many permutations?
Right, how many permutations can you do? Right, so degeneracies are permutations. I actually kind of prefer degeneracy a little bit because they all have the same wavelength. See, that's the thing. They all have the same wavelength, and that's going to mean they're going to have the same energy. Okay, simple equation, but runs into a slight problem. So we're going to have to deal with that. And I'll show you how to do that. And the answer is the volume of the sphere, by the way. Just to go ahead and put that out there. Okay, so now of course if you have degeneracy, then you need to multiply that by the energy. Now, here's the thing. You know that it's the energy, we're talking about light and Planck's constant times the frequency. Planck figured this out. I think Einstein had something to do with that as well. And because I've been yapping about wavelength, the speed of light over the wavelength is the frequency. Just some E&M for you. Actually, maybe you had that in middle school physics. So there you go. Okay, I've actually got taken aside at one point. Maybe I don't teach this in the right order, but around 1900, when they figured out the equipartition theorem, they tried to use the equipartition theorem for the energy, and that's like completely wrong. It's like this famous mistake, kind of like cold fusion. It was up there with cold fusion in 1900. So I'm going to show you that mistake. This is generally, people generally see this, so I feel like I should cover it because, you know, if you're college educated, you probably should have heard of this mistake because it was very famous. Okay, anyway, but so we know that's the energy of light. So it looks like we're doing pretty well. Okay, but don't forget though, I noticed that, what is this, right? So I got to remember that I have got to sum up all the different modes, right? So 1, 1, 1, okay, that's 1, the energy is this, but then I got to do the 2, 1, 1, that's 3 times their energy, and on and on and on. Now there's a 2, 2, 1, and then a 2, 2, 2, and a 3, 1, 1, right? So what you got to do is sum up over all modes. And that starts from n equals n squared equals, actually that's 3 to infinity. Right, the lowest n squared is actually 3. A little weird, but anyway. Okay, so there you go. So it looks like we're pretty much there. Now, unfortunately, this by itself will be a little bit more complicated than you think. And now I've got to make it a little bit worse. Let's look back at this thing here. Okay, so how many waves? Let's go back to 1, 1, 1. How many waves are in there? Well, just look at it. How many photons? A wave is a photon.
No, there's 3.
Well, okay. So, by the way, nothing you say is going to be right, but I just want you thinking. All right. Well, how many did I draw?
3.
3. Okay, that's a reasonable answer. What about 1? Maybe it's just 1 because there's only 1, 1, 1, 1. Oh my God! 1, 1, 1, 1, 1. Anyway, so what is it? 1 or 3? 1. Okay, now think about this. Well, let's actually kind of think more about 3. And that's neither of the right answer. Right? Who says that? All right, there's one. Let's say that the answer you want to say is 3. And in fact, that's kind of what my gut would normally say to me. Let's think of the wave that's like this. So that means there's 1 of them. But why? How big is a photon? Wait, is there only room for 1 photon with that wavelength? How big is a photon? I mean, I think I can stuff more in there, don't you think? Anyone know how big is a photon? Any idea? Infinitely small? In a lot of equations, you actually do treat it as infinitely small, but let me give you a better answer. It's about the size of its own wavelength. That's actually a better answer. Just a little fact bomb out there for you. Okay, let me give you another one. How big is an electron?
10 to the minus 23.
Well, now we tend to, like when we solve Coulomb's law, do you ever take into account the size of an electron? No, you don't. What about the size of a proton? Right, in chemistry we tend to treat them as points, and points are technically infinitely small. Right? Anyway, so I'm just pointing that out, but they're not. They're not, right? By the way, that's what string theory is. More info bombs. Question.
Hold on, so if you have a wave that's like miles long,
What a wave that's what kind of wave? Like an ocean wave? Or?
no, like a radio wave.
No, a radio wave would be about a meter long.
Yeah.
Yeah, about a meter long.
So how does that correlate to the size of the proton or the photon?
It's about a meter. here's how I can prove that. What object generates a radio wave? Yeah, an antenna, a radio tower. How big is a radio tower? How big are they? Or an antenna, how big are they? About a meter. Or like radio towers for, right, the object that generates them has to be the same size. So that's about right, isn't it? Right, and that's why I'm saying these waves have to fit in this box. So anyway, like I'm kind of going off on a tangent here. It's just there's a lot of neat things, a lot of little factoids I think are kind of interesting. So my point is though that photons are kind of small. Even if we want to say that they're green, you do that in your homework. Like green is about 520 nanometers. Do you think that you could fit more photons than just one in the z direction? Right? You could. You could fit like really an infinite number in there. There's nothing that says it's just one because that's the number of sets, or three because I drew it that way. There's really an infinite number in there. There could be really an infinite number in there. I'm not saying that there is. In fact, the thing that determines the number of photons is the Boltzmann distribution. Okay. So there's a certain energy for each photon, and there's a certain probability that you'll have that energy, right? Just like there's a probability that a O2 is moving 300 meters per second, it's kind of at the higher end. There's a probability that an oxygen is moving 1,000 meters per second. There is a probability, it's just very low. There's a probability that a photon will have a certain energy. Whether it's low, like the waves I drew here, and then what you do is, the Boltzmann factor will then fix that. We'll then tell you how many photons are actually present. Anyway, I'm kind of jumping ahead of myself. So you can see here that this unfortunately got kind of complicated, right? So complicated that I'm going to spill until Friday to cover it. So, I think I notice as I age, I get slower and slower, but I also know that if you kind of get bored in here, I'm actually happier than, if your options are bored or confused, let's go with bored. And if it does get confusing, I would also understand that. I'm trying my best. But then that's why one of the reasons to video is a lot of this material, some of this material, like when I was just talking about separability and how the equations are all for x, y, and z are multiplied, that is one that I tend to just repeat it over and over again to get it through to you because I just find that to be the best way. Okay, now let's tell you what. Energy, hc over lambda. I've got the wavelength defined, so we're set there. Question?
I think your video it looks like it's fine.
Is it?
No, it's fine.
It's fine?
It's
It's just your angle. No, thanks for noticing that. You guys good keeping an eye on. Question?
Can you explain what the different orientations were significant again? Are those were significant, like the 111, 211?
Okay, so it's a degeneracy factor. So I know that I can calculate the cool thing about doing this nx squared plus ny squared plus mz squared, we call it n squared, is that it gives me a simple formula for wavelength. And wavelength and energy are the same thing, basically. It's multiply the wavelength. Anyway, cool. Problem. It introduces degeneracies. So I can calculate the energy of the 211 photon. N squared would be 6, right? So the energy of that wave is 2L over the square root of 6. Right? But there's 3 of them. There's three ways to do that. So you have to take that into account.
Gotcha.
Yeah, just like, seriously, it really is just like there's 1 s orbital, 3 p orbitals, 5 d orbitals. You can't forget that stuff. It matters. Okay, in fact, all right, energy is easy. Energy's easy. Let's do this degeneracy thing. This is kind of weird. So what I'm going to do is make a table. And I have a handout on this. I'm going to give it a few examples of some sets, and then the number in the set. Now, I'm not going to write down the wavelength because here's the formula for it. So in fact, it's right up there, so I'm not going to repeat it. I just want to remind you that I know this. This is the point of putting, and this is the energy. I just want you to just remember that I know this. Okay, the set 111 was rather simple. N squared is 3, and the number in set is 1. And then the wavelength is 2L over the square root of 3, and then whatever the hell that is. Anyway, probably a pretty small energy. Let's say you have like a 1 centimeter cube. Okay, now, I just went over this one, 2 on 1. See, 4 plus 5 plus 6, so N squared is 6. And the number in set is 3. And this is the thing we need to care about. And again, the wavelength is 2L over the square root of 6, and then that's that. So let's not worry about that. Okay, so whatever. Now here's the thing, what I'm trying to do, let's go forward here. Let's think about like 60, 60, 60, 60. And that would be 10,800. Running my calculator right before class. And now, I should have done this here too, right? That means that there's others. 428, 100, 1260, 14, right? Adds up to 10,800, right? So there's a bunch of these. In fact, there's 28 of them. So, right, you get the idea. Now let's how about the set 200, 200, 200? And by the way, when it comes to light, visible light in a light bulb, these mode numbers are like 10 to the 9, by the way. So, okay, 200 cubed times 3 is 120,000. And I had to use a computer to do this. There's 37 other numbers that add up to that squared add up to the same thing. They have certain wavelengths and certain energies, yada, yada, yada. Okay. All right, so. Now remember, our goal of total energy is defined. Degeneracy, what I'm trying to do is come up with a formula for these degeneracies. And if I do that, I'm kind of home free, except for this Boltzmann thing. We've covered Boltzmann thing, but anyway. So I want a formula for this. And it turns out we're running into the same problem, as I already mentioned, partial x, partial y, partial z. How did I turn that into partial net? Right? It turns out that it's identical to this. Let me plot partial x, nx. It doesn't matter if it's a partial. I shouldn't be rambling about partials now. That's a problem. Okay, so let's make these, it goes from 1, 2, the mode numbers go from n equals 1, no nodes, n equals 2, 1 node, n equals 3, 2 nodes. It's a little weird there, right? So that we don't run into a 0. So let's move out here in y and z. Notice that we're in the first quadrant. And what we're doing is we are actually creating a volume. We're creating a volume. We're creating the volume of a sphere. It's actually 1/8 the sphere, right? Because it's in the first quadrant. There's no negative mode numbers. That doesn't, negative number of nodes, that doesn't make sense, right? So what I have created is for the net n, and I'll just have that touching some weird spot on the surface of the sphere in the first quadrant. We are creating a volume, just like we did when we did partial x, y, and z. Same thing. Okay, so here's the thing. What this does is, this is a little funky. Again, it gets a little funky. It turns out that, okay, so this volume of a sphere, which is 4/3 pi n cubed, let's do 1/8, because remember, first quadrant. I'm glad you guys are kind of more a bit mathematical, so you know what quadrant means, right? So we're in the first quadrant, so that there's 1/8 volume of the sphere. What does this give me? Again, it's a little nuance. If I plug in 6, if I plug in n squared of 6, let me back up. If I plug in n squared of 3, the answer is 1. If I plug in an n squared of 6, the answer is not 3, but it's 4. What it does is it gives me a running total. So the volume of this 8th sphere gives me the number of modes for whichever one I'm talking about, the number in set, plus all the others. Now, the reason that is look, when we're out to like, let's say that we've moved so far that we're like at 200, 200, 200. The surface area is like this, but the volume contains all that other information as well. So that's how that works. So again, this is total degeneracies. You know, the sum is the sum of them all. It's a little bit of a nuance, and I kind of hate to complicate this. It's not even that important. It's just that is what it is, and I don't want you to like mess with this and figure out something's not quite right because I tried to like cover up the difficulty. And I'll show you how you deal with that fact. I know, you know, when I was reading the derivation, what I wanted was a formula. You know, give me n squared and give me the number and set. And there really isn't a function for that. There's a function that gives me that plus all the others behind it. So that's what I have. Okay, now so what? Okay, so this volume is, let's see, that is actually 1/6. 1/6, where in my notes, 1/6 pi, 6 pi, and x squared plus ny squared plus mz squared. Okay, so this is a little funky. This is n squared, so to make that cube, I have to raise it to the 3/2. That's what I have to do. Okay, so a little weirdness there, right? So if you get a little confused at that, if you get a little confused, let me just point out. How can I do this? So I need 4/3 pi n squared n cubed, and to get that, I take the square to the 3/2 power, and that is for there we go. I should have, sorry, I'm not as well organized as I should be. There you go. All right, so you see how I derived that? It actually, I swear, I always get a little confused on this stuff. It's very simple, right? This is obviously 1/8 4/3 pi n to the third. N to the third is n squared to the 3/2. And I'm doing that because I have this formula for n squared of nx squared plus ny squared plus nc squared. That's why I do that. Anyway, in case you get a little, I don't want you to get confused on a single step, because, you know, when you're doing a proof and you don't follow a step, you actually don't have it, right? That's the, you know, it's cool that you can do this perfectly step to step. What sucks is if you get confused on a single step, you're kind of dead. Okay, anyway. Now, back to this. Okay, this ends up being pi over, okay, let me just point this out, that this ends up being 4L squared over lambda squared to the 3/2. And that is coming from, right up there. Yeah, n squared is 4L squared over I have some weirdness in my notes. Why do I have that? Sorry, what have I done? I've made a mistake, haven't I? Why is that 6 to 3? Let's see here. So I've got n squared. This is n squared, and that's 4L squared over lambda squared, right? So I'm pretty sure I've done that right. So I'm guessing that this is a 6. I don't know what I've done wrong. So I'll have to figure that out next time. Okay, let's continue working downward, and thank God I've only got 10 minutes left because I'm obviously getting flummoxed. Actually prep this lecture. There's some lectures I have to prep for 2 or 3 hours because it's so confusing. There's so much stuff, so many constants. The Carnot cycle, that was one. I have to prep a long time for that one, you remember that. Let's see here. Okay, let me see if I can actually just figure it out while I'm stating the jibber jabbering. Okay, so, what if I do? I've got 1/6, right? Okay, so what is 2 to the 3 halves? Anyone got a calculator? No, 4 to the 3 halves. I want to take that 4. I'm thinking that's why I'm going to take 4 to the 3 halves is 8, right? Okay, so yeah, so this so the volume I'm just working down is 8 pi over 6 L to the 3 over lambda to the 3. And does this get me? Yes, this gets me back to where I was. 4. I'm doing middle school algebra here. Okay, so again, now I've got a simple formula for the degeneracies. I've got a simple formula for the energy, so I'm almost home free, except, wait. There are 2 polarizations. 2 polarizations of light. Now, I think this is on your 3rd homework. Did any of you have a chance to look at it yet? So I have you do a little bit of this on your next homework. It turns out that there are 2 fundamental forms of light. 2 polarizations. What do you think they are? X and Y, or you know because you already looked, right? Circularly polarized light. Who's heard of this before? You guys heard of circularly polarized light? No, some of you know. Some of you haven't. Okay, here's what's happened. You think of light as moving up and down, right? So you can think of, imagine there's an arrow pointing at my finger from the center, right? So it's pointing up, and then the arrow's pointing down, then it's pointing up, and it's pointing down. That's how light is? Isn't that how light? That's actually wrong. That is not how light works. What we told you is a simplification. Here is how light moves, and then I'll do it this way, and I'll do it at you. Light, now remember, light's a vector, so you can think of it as I'm pointing up and down. So this is what I'm doing with my pointing vector, right? So that's what I'm doing. And that is not true. That is not how light works. How light works, it actually does this. Light actually rotates about its direction of propagation. That's circularly polarized light. But notice that I did, I think this is technically left hand, even though I'm doing it with my right hand, that's a little counterintuitive. If I can do it that way, then I can also do it
So clockwise and counterclockwise.
clockwise, counterclockwise. That actually is more useful than what I would say. Thank you. Let's do that at you, right? That is left, actually circularly polarized light, and this is right. That is the natural form of light. That is how photons are. When I drew this like I did, like a plane, that's actually an approximation. That's not true. And I do that because how the hell else am I going to draw circularly polarized? How would I draw that? Actually, look on your homework. There are ways of doing it. Just, you can draw 3D vectors in 2D space. So anyway, circularly polarized light is the real form of light. And therefore, it's like an extra degeneracy factor. And so what you have to do is 2 times. And so now we have 8/3 pi L. That's the degeneracy factor. Okay, so notice that we're on our way in a big way. Okay. Now here's the thing. Remember our big goal. What is the energetic output of a light bulb, of this weird square light bulb? What is the energetic output? I need to know the energy of the light, which is hc over lambda, so I got a good formula for that. But I got these degeneracies, but now I've got a good formula for that. So I'm actually almost done. But I want to point out, though, that when I was reading this, I had this formula, I mean, it's right there, And I also had been making this table, and I noticed it doesn't quite work. So seriously, I mean, for one, these ends come in like 1, 2, 3, and this function is continuous. Here's another way of putting it. The wavelengths, notice that this is like, oh, plug in the wavelength. What wavelength? Not every wavelength fits inside the cubic light bulb, right? Here's the lowest wave, right? Because it fits inside the box. Here's the lowest wave. Not one that's too long, right? So not every wavelength fits inside of here. So that's why this formula is actually flawed. This approximation that I'm making, which you've probably just accepted as like, oh yeah, that's how it works. It's not really correct. It's an approximation. Let me show you how bad it is. Now, I want to point out to you there's a handout on the website and the resources where I used a computer algorithm to figure out the real number of modes. That's actually how I generated these numbers here. Real number, total number of modes, by the way. And I divided that by 8 pi L to the 3 over 3 lambda cubed. So that's the y-axis. And on the x-axis is n squared. And when you get to about 10,000, okay, there's 1.0. When you get to 10,000, it becomes pretty close to correct. It's always slightly below it. It's always slightly below it. But there you go. Now again, I do this on a handout on the website, so if you want to see exactly how this works, this whole degeneracy volume of the sphere, 1/8 volume of the sphere thing is an approximation. And look at the website to see how bad an approximation. It's not bad at all when you hit n squareds of about 10,000. Now, as I mentioned to you, when you do this for real, got 10 to the 5, you hit n squareds of 10 to the 9. That's the space you actually work in when you solve this sucker for real. And there you go. Actually, so let's just go ahead and end there. Bring up your homework. So again, what we're going to do next time is take this thing times the energy and do the sum and get the energy of a light bulb. But that takes about another 20 minutes, so I'm going to go ahead and stop there. And so I'll see you all.